All right, well, welcome back to another fun-filled day of trig. So last time I was showing you, we finished up our talk of the inverse trig functions, did a little mixed composition stuff, and then we went to looking at how we can use identities to simplify and to create new identities. And that's what I want to do today. I want to continue with that, show you a couple more examples, show some techniques, and then introduce you to another set of identities that have to do with, adding and subtracting angles. So before I go there, any questions on the homework? Is everything in there going all right?
I do have questions on the chapter 8 review, but that's something that I would like to talk to you tomorrow when I have office hours with you.
Okay. I look forward to that. Anything else people would like to discuss? Okay, well then what I want to do is start with just a little bit more of the how do we prove identities? How do we show identity? So I just want to remind you the general steps. What we want to do is start by picking a side, right? And I say pick the uglier side. That is a little subjective, but ugly usually means there are things that we can do with it. As we progress, I'll give you more my definition of ugly. But we pick a side and we work only with that side. We don't move anything to the other side. We don't bounce back and forth, because if we do that, if we start moving things one side of the equation to the other, we're assuming that it's true. And proving something is true by assuming it's true is not good, right? That we don't do that. So you want to start with one side, work with that side only until it looks like the other side. And so I showed you a bunch of things we did last time that were algebra, lots of algebra, factoring, adding and subtracting fractions, breaking fractions apart, foiling things out, right? There's a lot of algebra there. There's also some trig, but I want to show you a couple of more techniques, things that are going to pop up that, well, one of them for sure is not obvious. Okay, so let's go to the board and I'll go ahead and show you what I'm talking about. So here's an example of an identity that I want to try to prove. Now, in terms of how this looked compared to some of the others, it's not terrible. We've got cotangent of x minus 1 over 1 minus tangent of x. And what we want to show is that that actually equals the cotangent of x. So first, just as a justification, you can see why this might be nice. Instead of having this horrible fractional thing with cotangents and all that, we could just rewrite it as cotangent. So that's something that would be very, very beneficial in the long run. Okay, so the technique for this one is one that I hinted at, and I don't know that we really did any last time, which is turn everything into sines and cosines. So that's what I'm going to do here. I'm going to start, the ugly side, I think we could all agree, is the left. It's got a fraction. It's got tangents and cotangents, right? It's not that pretty. So let's work with that side. And what I'm going to do is I'm going to start by turning all of these, cotangent and tangent, into sines and cosines. Because check out what happens if we do that. So cotangent, if we use that quotient identity, that's cosine over sine. And then tangent, of course, is sine over cosine. So here's where we get when we just turn those things into sine and cosine. Well, now comes the algebra. What we want to do is try to simplify this. And I don't know if you remember when you have complex fractions, that's a fraction inside of a fraction. One of the really good techniques, there are really two things you can do. One is you can actually combine the fractions on top and on the bottom, and then you have one fraction divided by another so you can flip and multiply. Or You can multiply by the common denominator, the least common denominator of what I call the sub-fractions, these guys that are inside. And that's what I like to do, because what happens there is you immediately get away from having the fractions, like all the fractions are gone. So let's start by multiplying by sine and also by cosine. So we're going to take the top, multiply it by sine times cosine, and do the same thing on the bottom. So with the first one, when I multiply through, the sines are going to cancel. And so I'm going to get cosine squared of x. Right? The sines cancel, and then I have cosine times cosine. And then I'm left with minus sine of x times cosine of x. And then on the bottom, when I distribute, same kind of thing. Sine cosine times 1 is sine of x cosine of x. And then with the other piece, the cosines cancel, and I'm left with just sine squared. All right, so the first step was really just a trig step, try to get us into sines and cosines. Maybe this will help us. Then we did an algebra step that brought us here. So now the question is, what do we do next? Any thoughts on this one? What might be a good next step? And while crying is always an option, we try not to go with that one. Well, I think it's time for another algebra step. Another one of the dreaded F words. How about we factor? If you look on top, you'll notice that there's a cosine in common with the two terms. And on the bottom, there's a sine that's in common with those two terms. I'm going to factor those out. And there's really two reasons. One is I can, right? Factoring is something that I can do. It's a step I can at least try if I know anything else to do. But probably more importantly, something that's suggesting I want cosine by itself up top and sine by itself on top is the where we're heading. Come back and look up here. Remember, what we're trying to do is to make this ugly side look like cotangent. And we know that cotangent can be written as cosine over sine. So that's really what's driving me towards, hey, can I get a cosine on top? Can I get a sine on the bottom? So let's try that. Let's see what happens when we factor those things out. So on top, when I pull out a cosine, I'm going to be left with a cosine minus a sine. And then on the bottom, when I factor out the sine, I'm going to be left with a cosine minus sine. And this is when everybody should get really happy, because now we have a factor that's in common that can be canceled. So I'll grab my red slashing pen, cross those guys off. And so what I'm left with is only cosine over sine, which by the quotient identity, I know is cotangent of x. So victory, we just showed that cotangent of x minus 1 divided by 1 minus tangent of x is actually just cotangent. So in the future, if you're ever presented with cotangent minus 1 over 1 minus tangent, go ahead and change it to cotangent. Yeah, I know. You're probably never going to run into that again, or remember it, actually. but we know for sure that it does simplify this way. So again, look at this and look at what was trig versus what was algebra. We did trig exactly twice. The first was in that first step when we changed things into sine and cosine. And the one other time we used trig was the very last step. So first and last step were trig, all the rest was algebra. So like I warned you last time, this is algebra, 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 algebra. The stronger you are with algebra, the easier this is going to be. All right, but the point of this one was to show you that if nothing else, turn things into sine and cosine. It usually gives you ideas of things to do, like there was an obvious algebra step after that. So it can give you a push, and it often will get you where you need to be. All right, so any questions on this one before I erase it and show you another? Looks like we're good. Okay, so here's another one. Let's look at this guy and see if we can prove that this is an identity. So we're going to have sine of theta over 1 plus cosine of theta. And we want to show that that's actually the same as 1 minus cosine divided by sine. All right. So first of all, this is an identity. If you were to plug angles in, you'll see you get the same thing on both sides. If you were to draw the graph of what's on the left or the graph of what's on the right, they're going to look the same. So we know it's identity, but we still want to show it. So think about things that I've suggested. First of all, we have to pick a side. Which side's ugly? Or maybe uglier, because they're probably both ugly. Does one side look worse than the other?
The right looks a little worse than the other.
All right, so why do you think the right looks worse?
Because with you have cosine and on top and sine theta. For that, it's making me think of like cot.
Okay, so it definitely would give us a cotangent if we were to split it apart. But you could algebraically split this apart as 1 over sine minus cosine over sine, which would give you a cosecant minus cotangent. All right, there are a couple of you saying left. Left is uglier. And then Kai says the negative on the right makes it uglier. Okay, so I think this one, it's not really obvious which side is uglier. And I would argue that they're pretty much equivalent. They both have fractions, right? Fraction is usually something that tells me ugly or not. Neither one of them has things other than sine and cosine, which usually is something that makes it uglier or not, right? So these are about equivalent. All right, so it doesn't really matter which side we pick. I'm going to start with the left, only because it's closer to me, so I don't have to write way over on the other side of the board. We could easily use the right instead. Okay, so here's what I'm going to do for my first step. Obviously, there is no algebra to do because I don't have any like fractions that are being added. I don't have anything to factor or multiply out or anything like that. So what I'm going to do, I'm going to multiply the top and bottom of this fraction. And I'm going to multiply top and bottom of it by 1 minus cosine. And it's probably at about this time you go, what? Where the hell did that come from? So this is one that I like to call a miracle step. All right, this is the, where did this come from? The math gods smiled upon us and gave us this wisdom to miraculously multiply top and bottom by 1 minus cosine. Let me show you that it works, and then we'll talk about how you can actually get this divine inspiration on your own without having me channel it. All right, so watch what happens. On the top, I'm going to leave it as it is. I'm going to leave it in the factored form. We're going to have sine of theta times 1 minus cosine. I'm just going to leave it like that for right now. But on the bottom, notice that this is a difference of squares factoring. So when I FOIL it out, I'm going to get 1 minus cosine squared. The OI part is going to cancel. The outside is a minus cosine theta. The inside is a plus cosine theta. So they cancel. And we're left with just 1 minus cosine squared. All right, now, if you look at where we're heading, you notice that we do need a 1 minus cosine on top, and we've got that. But we need a sine on the bottom. And right now, I don't have any sines on the bottom. I only got cosine. So is there a way we could turn those into sines? Anybody maybe recognize an identity that involves sine and cosine? Maybe specifically a square of a cosine? How about the Pythagorean? Remember that one? One of the biggies. We've got that sine squared plus cosine squared equals 1. So if I were to rewrite this, move that cosine squared over, I get that sine squared is equal to 1 minus cosine squared. So this bottom, the 1 minus cosine squared, it's actually the same as sine squared. So we'll have sine of theta times 1 minus cosine theta over sine squared. So we were able to put sines into the bottom, which is what we needed. But we've got one too many. But luckily, the one too many is going to cancel with the one on the top that we didn't need. And what we're left with is 1 minus cosine over sine, which matches what we wanted on the other side. So this miracle step totally worked. Totally worked to multiply top and bottom by 1 minus cosine of theta. But I know what you're thinking. This doesn't help me when I'm going to take this test because I don't have Bruce with me and all that. All right, so Yair, real quick, you just said, does it work if it's positive? No. If we had tried 1 plus cosine theta, it would not have worked. It had to be 1 minus cosine theta. Okay, so that's actually a good question because it's not random, and I can't just, try anything because only certain things are going to work. But here's where this miracle comes from. It's all about looking at where we're going. So think about what I did. I started with the left-hand side, and I'm trying to see how I can turn it into the right-hand side. So basically, here was my thought process. Where I'm going wants a 1 minus cosine theta on the top, right? I mean, you can see that. We want 1 minus cosine theta. So what I'm going to do is put it in. I need it, so I'm actually going to put it in. And I can put it into this fraction by multiplying. So I'm going to multiply by 1 minus cosine theta. But that forces me to do the same thing on the bottom. And the next thing you know, it worked. So the miracle isn't a miracle, it's paying attention to what you need. I wanted a 1 minus cosine. So I put it in. Now, I want to show you that that's not the only way we could have done this. Because let me erase the multiplying by 1 minus cosine. And so I'm going to erase this. If you need to go back and look at it, check out the video once I get it posted. But what I want to show you is that was not the only miracle step that would have worked. Because what we also could have done is this. Instead of introducing a 1 minus cosine, I could have introduced a sine. I need a sine on the bottom. This right here tells me I need a sine on the bottom. I don't have one, so what I'm going to do is I'm going to put it in. So I'm going to multiply the bottom by sine, which means I need to multiply the top by sine as well. So that would have given me sine squared over 1 plus cosine times sine. Now the next step here would have been, okay, I need to get rid of the sines on top. What I want are cosines on top. So I'll use the Pythagorean and I'll rewrite this as 1 minus cosine squared over 1 plus cosine times sine. So it's the same Pythagorean. We're just substituting in for sine squared. So then the next step here would have been to factor that top because it's a difference of squares. So we get 1 minus cosine times 1 plus cosine. And at this point, we just have one more algebra step. We just slash off those 1 plus cosines. And notice that I still was able to turn it into the other side. So really what I did was I just looked to see what I needed and I put it in. And it would have worked whether we used the top or the bottom. Okay, so if you hear me talk about a miracle step, this is what I mean. This is Bruce language. But a miracle step is just you're introducing something that you want. Remember I told you mathematicians are sore losers. We don't like being told you can't do stuff. It's another great example. I really wish I had a 1 minus cosine. Okay, I'll put it in. And as long as you follow the rules, it's legit. In this case, the rule was if you multiply the top, you got to multiply the bottom. All right, so watch out for that. Watch out for a quote unquote miracle step. Sometimes you just put in what you need and hope that the algebra follows and gets you where you need to be. Okay, so there was just a little more to kind of review what we were doing last time. But what we want to do today, or what I want to do today, is actually show you another set of identities. So I'm going to switch screens real quick. Because I'm going to try something out. I got a new toy, a little art pad that lets me draw things on the computer. So I'm going to try to share the whiteboard that's available here in Zoom because maybe I can have a little more control over what I'm drawing here. So we're going to try this out. If it doesn't work, I'll go back to the whiteboard. But let's see how this goes. So I'm going to go ahead and share my screen, and we're going to go to the whiteboard. So in a second here, you should see the whiteboard. All right. So what I want to show you today is it's the set of identities that involve adding and subtracting angles. Okay. Now, what we're going to do is something very geometric right now. We're not going to do anything algebraic for a little bit. But let me just start over here by drawing good old axes and a unit circle. So just squint, that's a circle. Okay, now I want to put two different angles on here. I'm going to put an angle that I call alpha and an angle that I call beta. So let's start with this one. And let's just say that this is the angle beta. And then we'll use another color here to maybe make our alpha. So let's put alpha somewhere over here. So this is alpha. Okay, so the fact that they're in the first and second quadrants are kind of irrelevant. I just wanted these two guys. Okay, so now what I want to do is think about the points that are on the unit circle that occurred where those two angles show up. So in terms of their coordinates, we know exactly what they are. This one's going to be cosine of beta, sine of beta, right? By definition, we know the x and y coordinates are the cosine and the sine. So the other one over here, its coordinates are going to be, whoops, not sine, maybe cosine. So we're going to have cosine alpha, sine alpha. Okay, so that's that point right there. So that's just by definition. We knew that a long time ago. Okay, well now what I'm really interested in is not really those 2 points, but I want to look at the line segment that connects those points. All right, so see that pink line right there? Let's find the distance for that length right there. Okay, so we're going to go ahead and write out the formula for that distance. So we're going to use the distance formula, call it d. It's going to be the square root of a whole bunch of stuff. And the way that we do this is we take the difference in the x coordinates and we square them. So this is going to give us cosine of alpha minus cosine of beta. Oops. We're going to square that. So that's the x coordinates. And then we're going to add to that the same thing with the y's. Right? We're going to take the difference in the y coordinates, which are going to be the sine of alpha minus sine of beta. And that whole thing squared. So that's good old distance formula from way back when, algebra, right? Distance between 2 points. Now, we're going to simplify this a little bit. So if I FOIL it out, I'm going to get cosine squared alpha. I'm going to get a minus 2 cosine alpha cosine beta. And then I'm going to get plus cosine squared beta. So those are the terms from this one. And then from the sines, we're going to get something similar here. We're going to get sine squared alpha minus 2 sine alpha sine beta. And I need to write down here below, plus sine squared beta. Okay, so that's all under that square root. So I know that's ugly looking, but it is going to simplify down for us. Because notice, let me do some circling here. I've got a cosine squared alpha, and I also have a sine squared alpha. What do I get if I add those together? All right, good. We'll just put in there, it's 1, right? Sine squared plus cosine squared is equal to 1. And then similarly, I've got a cosine squared beta and a sine squared beta. Those also add up to 1. Okay, so if I simplify that, I get the square root of, it's going to be much nicer now, 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. All right, so yay. From this picture over here, just connecting those 2 points, looking at the distance, we get this right here. Okay. So any questions on that? I mean, well, probably the question right now is, why do we care? Right? But at least from that, we're good with getting that formula. Okay, so here's what we're going to do. So remember those 2 angles. We're going to take this same picture, so the same unit circle picture, but we're going to rotate it. We're going to rotate it so that the red line, the one that formed beta, is now on our x-axis, and the blue line, the one that formed alpha, is now going to be up here somewhere. And I'll even go ahead and put that pink line on there too, just so you can see where that still is here. So that goes from this point to that point. So you cool with what we just did? We literally just took this circle with those points and we rotated it so that we're here. Okay, so I did this for a reason, because now I want to know what are the coordinates of those same 2 points so that we can do the distance formula again. So the one that's on the axis, that's easy. That one's just 1, 0. Right? We're on the unit circle and we just went 1 to the right. The other one, now this one's kind of gnarly, so let me see if I can do it. This is going to be the cosine of alpha minus beta, comma, sine of alpha minus beta. So you'll notice that it's got a cosine. It's also got a sine, just like always, so x and y. But the reason that it's alpha minus beta is because this angle down here, so if I were to draw it, that guy right there, it really is the distance from the, the rotation from the red to the blue, which if we go back to the original picture, well, that's the extra we need to add to beta to get to alpha. So that angle is actually alpha minus beta. All right, well, let's do the distance formula again. So we're going to run over here. So this is going to be take 2 on the distance. So I'm just going to put a little squiggly here so we remember what we did already. But here's what the new one's going to look like. It's going to be the square root of, again, difference in x's squared. So cosine of alpha minus beta minus 1, and that whole thing squared. And then I'm going to add to that the difference in the y's. So that's going to be the sine of alpha minus beta minus 0. squared. Okay, so let's do similar algebra that we did before. So we'll have square root of a whole bunch of crap. This is going to give us cosine squared of alpha minus beta minus 2 cosines of alpha minus beta plus 1. So that's the squaring of this first thing. And then the second thing, it's kind of nice since it's minus 0, we're just squaring the sine. So we get sine squared of alpha minus beta. So this one doesn't actually look nearly as bad, but that's really because, well, there's less stuff that showed up. All right, but we can do exactly the same thing we did last time. We can play the little trick of notice that there's a cosine squared of alpha minus beta and a sine squared of alpha minus beta. The fact that it's alpha minus beta doesn't matter. We know that no matter what the angle is, cosine squared plus sine squared is going to equal 1. So I can actually turn that into a 1, which then makes this the square root of 2 minus 2 cosine of alpha minus beta. And the 2 right here came from the 1 from the cosine squared and sine squared plus that other one that was just floating right here. All right, so thanks for the geometry lesson, Bruce. This doesn't really help us much, except we do know that these two distances are the same distance because they're the same pink line. So I can actually equate those. Well, since they're both square roots, I know what's inside the square roots have to be the same. So let's just take what's inside those square roots and set them equal to each other. So I'm going to clear some space over here. Let me just go erase what's going on this side. And I'll erase the other picture while I'm at it. All right, so let's do that equation over here. So we now have 2 minus 2 cosines of alpha minus beta equals 2 minus 2 cosine alpha cosine beta. Give me 1 second here, I need to erase a little bit more. And then minus 2 sine alpha sine beta. So that was just coming from equating those two distances. And now we get to do a little bit more reduction. So you notice that there's a 2 on each side, so we'll cancel those. And then everything else has a minus 2 on it. So what I'm going to do is I'm going to divide by negative 2. Right? And as long as I divide everything by the same number, we're good. So what that's going to do then is cancel those minus 2's, and what we're left with is cosine of alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. And we're going to go ahead and put a box around that, because that, my friends, is the first of the sum and difference of angles identities. Okay, this is going to be the first of 6 that we get. Okay, so get ready for more. But there's the first one. So what this says is that if you have two angles that you're subtracting inside the cosine, it turns out you can't just do the cosine of one minus the cosine of other. You actually have to follow this process right here, which gives us the product of the two cosines plus the product of the two sines. All right, well, it is what it is. We know that it definitely works because we just proved it, right? We used geometry to prove it. But what I want to do is I want to go to the whiteboard. We'll come back to this. We'll come back to this electronic whiteboard in a second, but I want to go to the physical whiteboard because I want to use this and I want to show you what we can do with it. So I'm going to stop sharing. And let's go back to the board. All right, so we've got, let me rewrite it. We got the cosine of alpha minus beta is equal to cosine alpha, cosine beta, plus sine alpha, sine beta. All right, so why this is useful is something like this. What if I asked you to tell me the cosine of 5 pi over 12? All right, now this angle is not one of our nice angles, right? If you go and you look at our chart, 5 pi over 12 never actually shows up as a nice angle. But what I can do is I can write it as a difference of nice angles. So check this out. What if I were to write this as the cosine of 9 pi over 12 minus 4 pi over 12? Now, before we get to the where the hell did those numbers come from, just notice that this actually is the same, because if I take 9/12 minus 4/12, I get 5 pi over 12. Now, why I chose these two specifically is that they reduce to angles that we know. If we divide 9 and 12 by 3, we get 3 pi over 4. And 4 and 12, that reduces to 1/3. So we get pi over 3. So the cosine of 5 pi over 12, that's the same as the cosine of 3 pi over 4 minus pi over 3. So now let's use our identity. We're going to put 3 pi over 4 in for alpha and pi over 3 in for beta. So this is going to equal the cosine of 3 pi over 4 times the cosine of pi over 3 plus the sine of 3 pi over 4 times the sine of pi over 3. And we know every single one of those. Those are all on our chart. So those are the special angles. So we can get them. So the cosine of 3 pi over 4 is minus root 2 over 2. Since it's got a 4 on the bottom, you know it's going to be a root 2 over 2. You can just figure out plus or minus by looking at which quadrant it's in. Since it's second quadrant, I know cosine is negative. So that's minus root 2 over 2. And then cosine of pi over 3, I also know that. That's 1/2. All right, sine of 3 pi over 4 is positive root 2 over 2. And I also know the sine of pi over 3. That's root 3 over 2. So this ends up being minus root 2 over 4 plus root 6 over 4, which I can combine into 1. And I'm actually going to switch it so that my positive one comes first because I like that better. But here is the value of cosine of 5 pi over 12. So because we have this difference of angles identity, we're now able to find the value, the exact values for other angles that are not on our list. And in fact, now you're good for any over 12. So if you want cosine of pi over 12, 3 pi, well, not 3 pi, 5 pi over 12, 7 pi over 12, 11 pi over 12, all the ones that we don't already know, we can now find their exact values. Don't bother trying to memorize this because we don't use it all that often. It's not nearly as often as the other special angles, but we basically expanded how much of the circle we can calculate. All right, so there's cosine of alpha minus beta. So what we're going to need to do is develop identities for cosine of alpha plus beta, and also for the sines and for the tangents. But let's take a real quick break. I know that this stuff really messes with your mind, turning it into Swiss cheese. So let's take like 5 or 6 minutes. I'm going to go run, get a drink. But go stretch, do a mental stretch, something, grab a coffee or whatever, and we'll be back in a little bit. So what I'm going to do is I'm going to quit sharing my video, and you'll know I'm back when I start sharing. Okay, so I'll be back in just a little bit. Take a real quick run around the house, and I'll see you in a few. All right, so before we get to the other identities, I want to go ahead and get a secret word of the day for today's lecture. So in the usual looking around the room and seeing what I find, I think I may have told you I'm in my older son's room, and so I just randomly found on his shelf a cute little onyx dolphin. So the word of today is dolphin, as in the Miami Dolphins, right? Or porpoise. So dolphin, word of the day. All right, so let's go and develop the other identities. And specifically, we're going to be looking at the identities for sum of angles for cosine, and then similar ones for sine. So I'm going to go back and share my screen again. We're going to go to the whiteboard, see if we can kind of continue where we left off. So we already had the cosine for the difference of angles for cosine, right? The identity for the difference. Now, for the sum of angles, here's what we're going to do. We're going to want cosine of alpha plus beta. But we're going to be tricky here. We're going to turn this into a subtraction. So we're going to turn it into a subtraction by doing alpha minus negative beta. So this is like another super awesome trick in the math world, is turn addition into subtraction. So that allows me to actually use this identity. But what I'm going to do is everywhere there's a beta, I'm actually going to put negative beta, because that's what I'm subtracting. I'm actually subtracting the negative beta. So this is going to give me cosine of alpha times cosine of negative beta plus sine of alpha, sine of negative beta. All right, well, I don't want these things with negatives. So what I'm going to do is I'm going to make use of the even and odd properties for sine and cosine. So don't know if you remember this, but cosine, it's an even function. And even function means that when you plug in a negative, you get the same thing out as if you put in the positive. So let me circle those. So this cosine of negative beta, it turns into a cosine of just regular beta because of the fact that cosine is even. Okay, so even function lets me do that. All right, well, similarly, the sine of negative beta, sine is odd. So what odd does is it allows me to bring that negative out front. So this step right here where we went sine of negative beta and it brought that minus sign out here, that's because this guy is odd. So we just made use of the even and oddness of cosine and sine. But what that does is that gets us now an identity for the cosine of alpha minus beta, or sorry, alpha plus beta. The cosine of alpha plus beta then is equal to cosine of alpha, cosine of beta, minus sine alpha, sine beta. And if you look at that, we'll box it, or, well, kind of box it. If you look at this one, compared to the other one, I want you to notice that the forms are almost identical, right? We had cosine alpha, cosine beta. This has cosine alpha, cosine beta. The first one had sine alpha, sine beta, so does this. But the one and only difference is the first one was plus, and the second one was minus. So it turns out that it's really easy to remember both of them if you know one of them. All you have to do is change the sign in between, plus or minus I, and you're good to go. All right, so we got this first identity by doing geometry. The second identity just sort of fell from it using the even and oddness of cosine and sine. All right, well, that's those two. But now, let's see if we can build one for sine. All right, so what I'm going to do is start up here, and we're going to look at sine of alpha minus beta. Actually, let's do sine of alpha plus beta. So we're going to try to figure out sine of alpha plus beta. Now, the trick we're going to pull here is we're going to turn it into a cosine. And I know what you're thinking. What? We're going to turn it into a cosine? Yeah, we're going to turn it into a cosine by using the cofunction identity. You know, I changed my mind. I am going to do alpha minus beta. I apologize. The algebra is going to be easier for us. So. But regardless, I'm going to use the cofunction identity, which says that this is the same as the cosine of pi over 2 minus alpha minus beta. So we saw that a long time ago. The fact that sine and cosine, these guys are related. We saw that there was that shift in their graph of pi over 2 or the right triangleness, right? We definitely had that. Okay, well now, let me just rewrite this real quick. We're going to write this as cosine of pi over 2 minus alpha plus beta. So I'm just going to distribute the minus sign. And the reason that I did this is because I want to think of those two, pi over 2 and the alpha. I want to think of those two together. Because now I've got two angles that are being added. I've got the stuff that's pink here, pi over 2 minus alpha. And I also have beta, which means we can run down to this identity that we just established. And in alpha, we're going to put what's in the pink parentheses. And the beta is going to stay beta. So this is going to look like, oops, I don't want pink anymore. All right, so this is going to equal cosine of pi over 2 minus alpha times the cosine of beta minus the sine of alpha, or sorry, pi over 2 minus alpha times the sine of beta. So again, I'm just using this identity. I'm just reinserting, changing the names. All right, yay. But now I want you to notice a couple things. First, this guy right here. We have cosine of pi over 2 minus alpha. We can actually use that same cofunction relationship to turn that into sine of alpha. So we now have sine of alpha times cosine beta. And then similarly, the other one, we had the sine of pi over 2 minus alpha. That's going to be the same as cosine of alpha. All right, well, let me box that guy. Because there's the identity for the difference of signs. Now, that one looks very different. It doesn't have the same structure at all, right? Like if you compare it to the ones we've done so far. Because the other two had cosine times cosine and sine times sine. These are a different product. It's sine times cosine. The other sine times cosine. So it definitely looks a little bit different, but it should be different because we're doing sine now instead of cosine. All right, well, if you want to get sine of alpha plus beta, you're going to do the exact same trick that we did with the cosine of alpha plus beta, where we subtract negative beta. But just to spare us a little time, and I'll just kind of talk through it. What it ends up being is sine alpha cosine beta plus cosine alpha times sine beta, which looks very much like the one above it. The only difference is that this one has a plus instead of a minus. So let me just talk you through it. I'm going to put in a negative beta, basically. Well, cosine is even, so it doesn't change. Sine is odd, so we bring the minus sign out front, and a minus times a minus is a plus. All right, so looks very different, but it's the exact same kind of idea. And just like with the cosines, if you know one of them, you can get the other one. It's pretty easy because all you have to do is change the signs. All right, so there's our sum and difference for sines. All right, well, let me go to the physical whiteboard because I want to do another example here. I want to save this stuff for later. So let's try this problem. Here's what I'm going to tell you. I'm not going to tell you what the angles actually are, but I'm going to give you some information about them. Okay? I'm going to tell you this, that the cosine of alpha is equal to 3/5. And I'll even tell you that alpha's in quadrant 1. So we know exactly where it is, and we know exactly how big cosine is. I'm also going to tell you that the tangent of beta, it's equal to 5/12. But beta, this is actually in quadrant 3. So you know it's in either quadrant 1 or 3 because it's positive, but I'm going to tell you it's in quadrant 3. So we don't know those angles. But what I want to see is, can we figure out what the sine of alpha plus beta is? So if I were to take those two mysterious angles and add them together, and then take the sine, can we find that value? And the answer to this question is yes, we definitely can. We just have to find the right information to do it. So what we're going to do is we're going to start with that sine of alpha plus beta identity. So what we just determined is that that's the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So in order to calculate this, I need to know the sine and cosine of each of these angles. So let's start with alpha. So I know cosine of alpha, but I don't know sine of alpha. Are we able to get sine of alpha knowing its cosine?
Yes.
Yeah, that should be a quick yes, because we've seen that if you know one trig function, doesn't matter which, you can get all the rest. All right, so in order to help us do that, I'm going to draw a triangle. So this will be the triangle for alpha. Now, this one is exactly right since alpha is in quadrant 1. I know this is exactly what it looks like. But remember, we can always do this for thinking of the reference angle and then use it to backtrack. So I know the cosine is 3/5. So that's my adjacent over my hypotenuse. So in order to find sine, I need to know the opposite side. But we've got the Pythagorean theorem. In fact, a lot of you probably don't even need the Pythagorean theorem. You recognize this as the 3, 4, 5 triangle. But from that, we actually know what the sine of alpha is. The sine of alpha is going to be 4/5. So we'll leave a space for the cosine of beta. But then we also know the cosine of alpha, that was actually given. It's 3/5. And again, we'll leave a space for sine of beta. But there's the information we needed for alpha. An alternative way would have been use the identities. Excuse me, use like the Pythagorean identity. But I find drawing the triangles a little bit faster. All right, so there's alpha. So now we want to do a similar thing with beta. So let's draw a triangle for beta. Now, this isn't actually beta, but it's the reference angle for beta. But I'm still going to draw beta here. So what we know about it is the tangent is 5/12. So we know the opposite over the adjacent is 5/12. So we'll put the opposite side of 5 and the adjacent side of 12. So again, we can use the Pythagorean theorem. And if you use the Pythagorean theorem, you get 13. So this is another Pythagorean triple, 5, 12, 13. Some of you may recognize that as a right triangle as well. All right, well now we need to get the sine and cosine of that angle. All right, well, sine is opposite over hypotenuse, which is going to be 5/13. And then the cosine is adjacent over hypotenuse, which is going to be 12/13. All right, so now we'll see if anybody's really been paying attention. Because what I just did here is wrong. What did I do that was wrong? And it's specifically about cosine and sine of beta. The alpha part is fine. It's the beta part that's a problem. Okay, so we can just put in there quadrants. Yeah, we have to pay attention to what quadrant we're in. Beta is in quadrant 3, which means cosine and sine are actually both negative. So we need to put a minus sign on those because we're not in quadrant 1. So be really careful with that, especially when you draw the right triangles, because it's super easy just to get lulled into, oh, all the trig functions are positive in a right triangle. But this is the reference angle, which means if we're somewhere else, like in the case of beta where we're in quadrant 3, we have to keep track of the signs. All right, well, now we're good to go. So if I multiply this stuff out, I'm going to get minus 48 65ths. And then I'm going to get minus 15 65ths, which when I put that all together, gets me negative 63 over 65. So again, even though I don't know what that angle is, I have no idea what alpha plus beta is. I do know that when I add them together, though, the sine is minus 63 65ths. So basically, just think of these identities as more tools. They're more tools that we're going to be able to use when we want to do other things, like in this case, find trig functions of angles that we don't necessarily know, but we do know about one of the trig function values for those angles. All right, so there's an example of another kind of problem that you can do with these that we used the sine of alpha plus beta for. All right, so we've got a sum of angles identity for sine, cosine. The next question, of course, is there one for tangent, cotangent, secant, cosecant? And the answer is yes. You can develop one for all of the 6 trig functions. But we're just going to do one more. We're going to find tangents, because if we've got the big 3, we know what to do to get the others. All right, so I'm going to go back to the electronic whiteboard. And we'll go ahead and develop the identities for tangent. All right, so here are those 4 identities. But what I'm going to do, we're going to start kind of over. So let me erase a lot of this stuff. And what we're going to do is we're going to find the tangent of alpha plus beta. And it turns out I'm not going to use the difference of angles identity, so I'm just going to go ahead and erase that as well. But here's what we're going for. I want the tangent of alpha plus beta. Now, the way I'm going to do this, the way I'm going to calculate it, is by making use of that quotient identity. That tangent is sine over cosine. And now we'll take the identity that we just developed for sine of alpha plus beta, and we'll divide that one by the identity for cosine of alpha plus beta. So this is going to look like sine of alpha cosine beta plus cosine alpha sine beta. So that was the identity for the sum of angles for sine. And then I'm going to divide that by the sum of angles identity for cosine, which looks like this. All right, so at this point, you probably look at that and go, that's not any better, right? That doesn't really help us much. But we're going to do another algebra trick here. And this algebra trick may not be one that you would think of. So it's sort of a miracle step. And where this comes from is, well, it really does what I want it to do. But what I'm going to do here is I'm actually going to multiply the top and the bottom by 1 over cosine alpha cosine beta. So if I do that on the top, I got to do that on the bottom as well. So again, one of those really common tricks, the multiply top and bottom by the same amount. Okay, well, let me go ahead and distribute it through to each piece. And then we'll simplify. So I'm going to get sine alpha cosine beta over cosine alpha cosine beta. And we're going to get plus cosine alpha sine beta over cosine alpha cosine beta. That's the top of the fraction. Okay, so then I'm going to need to do the same thing on the bottom. So I've got now cosine alpha cosine beta over cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. All right, so just an algebra step that seemingly came from nowhere. But watch what happens. So in this first bit, I've got cosine beta over cosine beta. Those are going to cancel. The second one, I've got cosine alpha on top and bottom. The first fraction in the denominator, everything cancels. So what we're left with then, once we do all that simplifying, we have sine of alpha over cosine of alpha plus sine of beta over cosine of beta. On the bottom, I've got 1. Since everything over here canceled, I'm left with just 1. And again, I've got sine alpha, sine of beta, and that's over cosine alpha, cosine beta. All right, but I bet you can see what's going to happen now. I've got a whole bunch of sines over cosines, so I can turn those things into tangents. And what I'm left with here is tangent of alpha plus tangent of beta all over 1 minus tangent of alpha times tangent of beta. So that's the one you want to box, because that's the identity for tangent of alpha plus beta. So again, it all came back to what we had already done for the sine and cosine of alpha plus beta. And then we just did some algebra on it and turned it into a relatively nice form. All right, well, there's tangent of alpha plus beta. So of course, tangent of alpha minus beta, I'll write that one up here. The tangent of alpha minus beta. It's going to be very similar. What it actually looks like, though, is tangent of alpha minus tangent of beta over 1 plus tangent of alpha tangent of beta. So again, you can go ahead and box that. And this comes from the same trick. We're going to put in a negative beta down into this. And so the ones with alpha don't change, but the ones with beta, tangent is an odd function. So the minus sign comes out front. And that's what changes those signs. But we see the same pattern that we saw before, which is that the difference between these two is just their signs. You notice that the signs change just like they did in the sine and cosine identities. All right, so now we've got sum and difference of angles identities for the big three. And like I said, that's as far as we're going to go with these, because if you wanted, say, the cotangent of alpha plus beta, you just take this and flip it over. Right? If you want secant, do 1 over cosine. You want cosecant, you do 1 over sine. So we don't need to actually develop those laws, those properties, because if we know the big three, we got the rest. Okay, so I'm going to stop sharing here. All right, so how do we feel about all those identities? Okay. Again, I know it's a lot of algebra, a lot of stuff that's going on. So I'm getting some confusing. Is it confusing? Why is it confusing? How about let me start there? Because I know a couple of you said that. Where did we get confused?
I feel like it's more of like a lot of steps and just remembering how to do things in algebra.
All right, I appreciate that. How about, and I think both of those statements are absolutely true. Like when we develop these identities, it required a lot, right? There were lots and lots of steps, and it did bring back all kinds of stuff. Like you think about where we started with today. Today started with just distance formula. Okay, so we got to go back to distance formula. In the distance formula, there was multiplying out polynomials. Okay, then we had to use the trig. We had to use the identities that we already knew, right? So, like Kai said, it's a lot to remember. It is a lot to remember, right? And so if you think about like the algebra, I don't know how to advise you on algebra because at this point, I kind of have to go with algebra has already been seen. You kind of have a handle of it. But yeah, it does require us to bring stuff back. But in terms of the trig, it's really important just to remember these fundamental relationships. And that's why I keep bringing them up all the time, like the Pythagorean identity. That relationship is huge. Today, you saw how many times we were able to use it to simplify stuff down, right? The quotient identity, tangent is sine over cosine. We use that all over the place today. Even and odd, the even and odd relationships we used again today. The cofunction relationships, that good old pi over 2 minus alpha kind of deal, right? That was there. So in terms of all, the one that I didn't tick off, my pinky, I guess, can be the reciprocal. We didn't end up having to use the reciprocals when we developed these, but that's because we only developed the big three. If we wanted to get identities for the other ones, we would have needed to use those. So the most important thing to get out of trig when we're talking about identities is these fundamental properties. What are the fundamental relationships? Because they're going to keep showing up. We're going to keep using them because it's the nature of the beast. I mean, it's what these things are. And the better you understand those fundamental relationships, the easier trig gets by far. And I think it gets more beautiful too when you start realizing that we've got all this stuff, but it all stems from one place, right? And even if you look at what we did today, every one of the identities we developed today came from that distance formula picture. It was geometry. We literally have been doing just geometry today. I know it doesn't feel like it, but it was a geometry question that we then used algebra to do. Are there other things about this that are making it confusing beyond the lots of steps and we have to remember everything from before? And really the reason I'm asking is I want to try to help clear up any kind of confusion so that when we go forward, we're not feeling like we're drowning, right? Because when you get that feeling, it doesn't go away, right? It just gets worse because now we put something else on top and something else on top. So I want to try to pull you up to the surface before we start doing more. So anything else people want to share as what was confusing for them? Yeah, Juan, that's a good point. Practice with the homework will help. The more, like when you use these, when you go and you do things like, finding the tangent of 13 pi over 12 and stuff like that, you'll start getting the feel for how these things are built. So that's definitely true as well. Okay. So what I'm going to do is I'm actually going to stop. I know we're way early, We still have like technically another 15 minutes or 20 minutes or something like that. But I want to stop because I think you guys need to stop. I think you've you've been blitzed with enough. But what I really want you to do is over the next couple days, I want you to definitely practice homeworks, go back and look at these, where the derivation's coming from, and review your algebra. If there's any algebra stuff in there that you're like, oh my God, I don't remember this, it's good that you recognize that you don't remember it, but you got to go back and learn it. Okay. And well, got to is a little strong, right? You don't have to do anything, but it will make your trig life and your subsequent calculus life so much better if you get that strong algebra basis. Okay, I'm gonna, nah, this can be on the record. You're gonna get a little, I'm gonna start turning into dad. I don't really like doing this very much, but sometimes there needs to be a dad speech, and algebra is one of them. So I know that most people don't like algebra. And I know that a lot of you, your goal is you got to get the calculus so you can do whatever the science is that you want to do. So really the goal is calculus, right? And you've probably had that in your mind all along, that I got to get my calculus, I got to learn calculus so I can do blah, 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 blah. And you see things like algebra and trig, the pre-calc stuff, as just sort of I just got to get through it so I can get to the calculus. And what you don't realize is that without all that pre-calc stuff, you can't really do calculus. Like, you can do the steps of calculus, but you can't apply it to anything. And for every single one of you that's thinking about engineering or science fields at all, you do calculus so that you can apply it. And that application requires, and this is a math term, by the way, it requires a shit ton of algebra. Shit ton, it's a little bit more than a crap ton. It's definitely less than a fuck ton, right? I mean, there's a ranking, but it requires a shit ton of algebra. And so if you kind of went through algebra going, I'm just going to speed through this, I'm not really going to learn it, I'm just going to get my, pass my class so I can move on to the next, you've really done yourself a huge disservice, because it's going to come back and bite you in the ass in ways that you won't even imagine. So start correcting that now. And I don't, like most of you, like looking at this list, this roster, I know like 3 of you. So this is not, I'm picking on anyone in particular. It's just my experience as a calculus teacher and what students have done, coming through in the past. If you're one of those that right now have real shaky algebra, because you just kind of have, done the minimum to try to get by, try to correct that now. Trust me, it's going to make next year so much better for you. Because calculus is going to really suck if your algebra is weak. All right, anyway, but I'm done preaching. I'm done preaching about this. So I'm going to go ahead and pause the recording,